operating point or Q point or quiescent point. What is meant by this? You take any semiconductor device, that may be diode or BJT or FET, okay, any kind of diodes like GNR diode, varactor diode, tunnel diode, right? We generally speak about the Q point, operating point. Means at what voltage and current that particular semiconductor device is operating. Okay, that point, the values of set of values of voltage and current at which the device is operating in or conducting in. That point is known as Q point. How to find it and further details we'll see. Okay, as of now I'm not writing the definition, we'll see that. Right, once a device is in conduction, we need to find out at what voltage and current the semiconductor device is operating in. That point is known as Q point. Okay, how do we find it? For example, I'm taking a simple diode circuit. Some input voltage is given R, and as the input is, okay, let us assume input is greater than the cut-in voltage of the diode, V gamma. Then definitely the diode is under conduction. Once the diode is in conduction, there is a current flow in the circuit and there is some voltage V across the diode. To be frank, the value of V varies between 0.5 to 0.8 volts if the diode is made of silicon. Okay, right, it is a variable. It need not be silicon, it can be germanium also. Germanium means 0.1 volt to 0.3 volts. Here I'm thinking of silicon diode. Okay, anything you can take it, just I'm saying. So V is not a fixed value. It can take any value ranging from 0.5 to 0.8 volts. That's it. Okay. Then what about the current? Current again depends, right? It can take different values depending upon input, resistor, V, etc. Now, if I take the loop equation to this particular circuit, let me take this as loop 1. So KVL2 loop 1 implies V input is equal to I into R plus V. I can write. Further, I can write I is equal to minus 1 by R into V plus V input by R. Why I write it so? Means, see, if I take the volt ampere characteristics of a PN junction diode, what we do? Current is taken along y-axis and voltage is taken along x-axis. In that context, if you observe this, it is looking like the straight line y is equal to mx plus c, where the slope m is equal to minus 1 by r and constant c is equal to input by r. So how does this line appear? It is a straight line with negative slope, something like this. Okay, here it is a straight line with negative slope. Slope is equal to minus 1 by r. Okay, keep it aside. Now we know that what is the current equation of a PN junction diode? I is equal to Is into e power V by eta Vt. Of course, minus 1 is there. I am not considering 1 because once the diode is in conduction, compared to exponential term, 1 is negligible. We are well aware of it. Then if you draw this curve, it appears something like this. Okay, it is like I is equal to Is into e power V by eta Vt, and green color one, it is like I is equal to minus 1 by R into V plus V input by R. Two straight lines. Which is correct then? One is from the circuit, right? The straight line is from the circuit, and the curve is from the device characteristics. Which is correct? See, so far, right, I did so many problems. Most of the times I use loop equations, node equations, etc. But I have not considered this exponential equation. Okay, what is the reason? We can. Okay, the thing is, right, here, first we define the operating point. I'm coming to that. Okay, I'm saying both are correct, but both are correct only with respect to a single point. See, if I take a particular point here, that may satisfy the straight line equation, but that cannot satisfy this equation. Or if I take a point here, that may satisfy the exponential relation, but that cannot satisfy this straight line equation. Is it not so? Then both are correct. Where do we take that? Both are correct. Means both are correct with respect to a single point, and that point is just nothing but this one. This is the only point where both the equations are satisfied. If it is a straight line, pointers of a point of intersection of two lines we take. Here one is curve and another is a straight line. Point of intersection of these two, curve and straight line, is just nothing but our operating point, which satisfies the characteristic equation as well as the circuit equation. So that point is known as operating point. I can write IQ and VQ. So it is a Q point, X coordinate is VQ and Y coordinate is IQ. Okay, set of values of voltage and current which satisfy the device characteristics as well as the circuit equation in which the particular semiconductor device is kept is known as quiescent point or Q point or operating point. So far, why I have considered only the loop equations or node equations or the circuit equations in which device is kept means internally, inherently, what I did is I'm writing some equations and taking some values for voltage and current means those values are also satisfying the characteristics of the diode. With that assumption only, so far we did all the calculations. I need not write this equation every time. So far what we do by default, what we take is I'm writing some loop equation, node equations and finding the voltage across the diode and current through the diode means it is under the assumption that the values of I and V we have got are satisfying the device characteristics also. With that assumption only I did so far. Okay, now I'm clearly specifying them. One is circuit equation, another is device characteristic equation, and only one set of values of voltage and current which satisfy both the equations. That particular point is known as Q point or operating point. Means the device is conducting at a voltage of VQ and a current of IQ. That's the meaning of it. Okay, now let me write the statement. Set of values of, I'll write it in the next phase. Set of values of voltage and current which satisfy device characteristics and the circuit equations in which the semiconductor device is kept is known as quiescent point. Means at that voltage and current, the diode or BJT or FET any device, right here, in this case semiconductor diode is operating. Okay, that is the okay. This is very important. It need not be diode. It can be any semiconductor device. This is what we take it. But every time we do not show the characteristic equations because they are non-linear. We just with an assumption that we are right by applying loop equations, node equations, we are getting some voltage and current of a particular semiconductor device means it is under the assumption that the values are also satisfying the non-linear device characteristics as well. Okay, do remember this point. Right. The next one is small signal model of PN junction diode. What is meant by this small signal model? Let's say this. Suppose I have a simple PN junction diode circuit like this. It is 2 volts, 1.3 kilo ohm, and V is the voltage across the diode and I is the current flowing through the diode. Then if V gamma is equal to 0.7 volts, it is given. Then what will be I? Implies V is equal to V gamma we are taking and I is equal to 2 minus V gamma by 1.3 kilo ohm, that is 2 minus 0.7 by 1.3 kilo ohm, it is 1 milliampere. It means we can say that the diode is operating at 0.7 volts comma 1 milliampere. We can say that. Okay, everything is fine. Okay, the supply voltage is greater than the cut-in voltage, so it conducts and V gamma is given. Okay, fine. Whereas I'm taking the same diode and I'm applying some AC signal where Vs is equal to 20 sin omega t millivolt, the same 1.3 kilo ohm, and V gamma is also same 0.7. If Vs is equal to this, then what about the current and voltage of the diode? As it is AC current, I am saying I and it is small v. Here capital letters are used as the current and voltage are DC. Here I am taking small letters. Okay. Then what about the values of, okay, what are the values of I and V is my concern. How do we find them? First of all, does the diode conduct? No. Vs maximum is equal to 20 millivolts, means 0.0 volts, for which the diode cannot conduct at all. Okay, so if I take, if right, Vs maximum, right, if I consider Vs maximum is equal to 2 millivolt or 0.02 volts, which is less than V gamma, implies there is no scope for diode to conduct. Even for peak value or maximum value of input. Diode cannot conduct. Implies, what about I is 0 and voltage across the diode is also 0. Simply we can say. Okay, there is no point of AC current and voltage across the diode. Whereas I am applying both DC and AC together. Same 2 volts DC, Vs same 1.3 kilo ohms, where Vs is equal to 20 sine omega t millivolt. Then does the diode conduct or not? Absolutely, the diode will conduct. Because consider Vs maximum. It is equal to, sorry, V input maximum I can say. It is 2 plus 0.02. It is 2.02 volts, which is greater than V gamma. And V input minimum, it is 2 minus 0.02 volts. It is equal to 1.98 volts, which is also greater than V gamma. Means for minimum and maximum values of input, the diode is in conduction. Implies for all values of V input, V input, which is just nothing but 2 volts plus 2 plus 20 sine omega t, or 0.02 sine omega t. Diode conducts. And current I, let me take this current as ID and this voltage as VD. And voltage V suffix D exist okay, both will exist. Then how do we write this current and voltage? So also we can take I suffix D is equal to IDC plus IAC, and V suffix D is equal to VDC plus VAC. Why I am writing it so? Because the input is a combination of DC and AC. Okay, or I will do one thing for much better understanding. This is DC. This is AC. So I AC and V AC. We can write it. Okay, if you apply, use only the DC source, then the current is possible. But whenever you apply AC source alone, we don't have any current and voltage. Whereas if you apply this AC along with the sufficient amount of DC, we can find the current through the diode. Then how do we find this AC, IAC and VAC? See, I can write IDC and VDC. What is IDC? With respect to the DC source, if you have only DC source, I can say IDC is 1 milliampere and VDC is equal to 0.7 volt. Okay, so where IDC is equal to 1 milliampere and VDC is equal to 0.7 volt. I can write it. But what about IAC and VAC? How do we find it? It is not superposition, friends, because superposition, when do you apply it? Circuit should not change. Okay. Whenever you have two sources, overall response is nothing but sum of the individual responses. If you apply them individually, diode cannot conduct for AC. Diode conducts only for DC. Then how can I use superposition here? I cannot. Superposition is not applicable here. Okay, that's very, very important point. I'm writing here. Superposition cannot be applicable here as diode does not conduct for AC. Okay, then how do you find, or how can we find IAC and VAC is my concern. See, whenever you take any system or circuit, you are applying two sources, maybe DC, AC or both AC, whatever it is. When do you say superposition? If you use one source, the circuit is not changing, whatever, right? You will get one result. And again, use the second source by removing this. What is the, how the circuit is responding, calculate the output. Then we take overall responses, some of the individual responses if the network is linear. Okay. Right, we know that superposition, some of the individual responses. But here what happens, whatever the circuit you are getting with respect to DC, the same circuit you are not getting with respect to AC. Then how can you apply superposition here? Two different circuits are appearing. So definitely superposition is not applicable here. Then how do we find it? How do we find, then how to find IAC and VAC is my concern. For that, let us take the equation I is equal to Is into e power v by eta Vt. Then if the current is DC, the corresponding voltage is also DC. You can write this way. And whereas if the current is a combination of DC and AC, the corresponding voltage is also a combination of DC and AC. Where ID is equal to DC plus AC, it is equal to Is into e power VDC plus VAC by eta Vt. It is further written like Is into e power VDC by eta Vt into e power VAC by eta Vt. Then what about Is into e power VDC by eta Vt? It is just nothing but IDC into e power VAC by eta Vt. We can write. Further, see, I mentioned small signal analysis. Okay, small signal model. Small signal in the sense it is millivolts. Okay, it's not like 1 volt, 2 volt or like that. It is millivolts. Small signal model. And what about that millivolts range? Means, right here in this model, what we take is eta is 1 by default values I'm taking. Vt is equal to 25 millivolt. by default eta is 1 and Vt is equal to 25 millivolt. Okay. Then suppose or if VAC is far less than eta Vt, means it is far less than 25 millivolt. It is possible because if you observe this circuit, you are giving both DC and AC, right? Suppose I give here some 20 millivolts like that, 20 millivolts AC, then there is a drop across the diode, sorry, across the resistor, and some drop across the diode. Okay, voltage drop across the diode will be definitely very less. Okay, it is less than 20 millivolts, and which is chosen to be already less than eta. Okay, we are choosing the value of supply voltage in such a way that voltage across the diode Vd is very much less in comparison with eta Vt. So if VAC is far less than eta Vt, it is possible eta Vt is 25 millivolt and VAC may be some 5 millivolt or 10 millivolts like this. If that is the case, VAC by eta Vt is far less than 1, or VAC by eta Vt is far less than 1. Okay, what for I am writing all those things? See, we know, okay, why I am writing so means we know e power x is equal to or approximately equal to 1 plus x if x is far less than 1. Okay, if x is far less than 1. Similarly, VAC by eta Vt is far less than 1. That is like our x. Then which implies IDC plus IAC is approximately equal to IDC into 1 plus VAC by eta Vt. We can write like this. E power x instead of x, I have VAC by eta Vt. Then it is further written like IDC plus IDC by eta Vt into VAC. I can cancel IDC and IDC, which implies IAC is equal to IDC by eta Vt multiplied with VAC. We can observe. See, actually the current is exponentially related to the voltage. Okay, but I'm writing current is linearly related to the voltage. When is it possible? If this condition is met conditionally, IAC is equal to IDC by eta Vt into VAC. That statement is conditional. That is true if and only if VAC is far less than eta Vt or VAC by eta Vt is far less than 1. Then only this approximation is possible. Otherwise, we can't. It is now further written like IAC is equal to 1 by RF into VAC. I can write it. What is meant by this? Which means, suppose I have a diode through which the current flowing is IAC and voltage is VAC. That VAC should be in the order of millivolts. Then its equivalent is written like a resistance RF, of course the same IAC and VAC, where RF is equal to eta Vt by IDC, known as the dynamic resistance of the diode. This is how we can define it. Okay, that RF value depends upon IDC. Okay, and much better detailed version. What we can do is, this is our VI characteristic plane. Okay, here, as we discussed earlier, operating point. Okay, let me write with respect to operating point only. Okay, I'll do one thing. Volt ampere characteristics. Here I wrote DC in green color, I think, for setting the operating point. And for characteristics, I wrote something like this. And later we set the operating point. IQ and VQ. Okay. So IQ and VQ are generally set with respect to DC signal. By applying proper DC, we are setting the Q point. Now, after setting the Q point, I am taking small elemental portion. Right? Of course, if you observe the range, here it is around 0.5 volt and the maximum voltage across the diode, it may be around 0.8. That's the range of voltage across the diode we can see. Now, with respect to operating point, I'm taking small elemental portion. Okay, so delta V with respect to the operating point I'm taking. And what about its range? Its range is millivolt. Very small. See, the minimum is 0.5, maximum is 0.8, in between a small elemental portion. With respect to that small elemental portion, I can even take the current as well. I can say this as delta I and this one as delta V. It may be in the order of microamperes. To be frank, I is in the range of milliampere. Okay, it is volts, but the range is from 0.5 to 0.8. Then, if I take such a small elemental portion of the characteristic, it looks like a straight line. Is it not so? It looks like a straight line instead of a curve because I took a very small elemental portion. For your understanding sake, I wrote this much. But to be frank, 0.5 to 0.8, a small elemental portion which looks like a straight line. Means within this zone, right, within this particular zone, within this particular zone, okay, I can obtain or I can write a linear relation between current and voltage. Okay, I'm erasing it. It's not looking so good. Okay, within that elemental portion, right, elemental portion, it looks like a straight line. And what is the slope of that straight line? This one, a linear relation I can able to write between current and voltage like this. A linear relation we can write between current and voltage of the IAC. It is like delta I is equal to 1 by RF into delta V. That's the meaning of it. Okay, if I take small elemental portion, we can write a linear relation between them. Okay, and if I raise the range of delta V and range of delta I, then what happens? VAC by, okay, eta Vt. If I increase the range of VAC, then VAC by eta Vt is not far less than 1, then I can't take this approximation. This becomes invalid if VAC is large. If VAC is very much small compared to eta Vt, VAC maybe some 5 millivolt or 10 millivolts like that, then 10 millivolts is far less than eta Vt 25 millivolt, then 10 by 25, okay, its value is very less, 0.4, so it is negligible in comparison with 1, 0.04. Okay, so that is the idea. Okay, 10 by 25, it is 0.4, its value is negligible or it's very less compared to 1. So in that context, right, if that range is very less, then only we can neglect it, otherwise we cannot. So you can write the same thing, RF. Okay, in other words, as I mentioned, this straight line which is a part of the curve, then how to obtain that slope of that straight line? Slope here is, what is the slope? It is minus 1 by RF. In this example, what is RF here? RF is equal to eta is 1, Vt is 25 millivolt, IDC is 1 milliampere. It is equal to 25 ohms. RF is 25 and slope is 1 by RF, not minus 1 by RF, sorry, it is plus 1 by RF. DC line, its slope is minus 1 by capital R. This slope is DC slope. Here the slope is minus 1 by R, where R is the circuit component. And we call this slope as DC load line. Why the name DC load line? I will come to that point. So see the difference between the circuit equations with respect to DC. With respect to DC, I is equal to minus 1 by R into V plus V input by R we took. So we got the DC load line. And right, AC load line I have not yet written. We will see that first, operating point. So by giving a proper voltage supply to the diode circuit, we are obtaining the operating point. Okay. And next, after setting the operating point, we are applying AC along with the sufficient DC. Right? We are applying this AC along with sufficient DC. 2 volts DC. It's not like a 0.5 volts DC or 1 volt DC. We are giving appreciably good value of DC, so that for all values of input, means combination of DC and AC, the diode is in conduction. If so, the current through the diode and voltage across diode are a combination of DC and AC. We know the DC component values, but we do not know the AC component values. How to find those AC component values means, it is conditionally we are taking the AC voltage across diode is far less than eta Vt, and hence the nonlinear relation of current and voltage of the diode can be approximated to a linear relation. Okay, we can write so. And the slope of AC is nothing but 1 by RF, small rf, where RF is equal to eta Vt by I DC. We can take so. This is very important. And this curve or this straight line is coming along this curve. So then how to obtain the slope of a straight line drawn along a curve, which can be obtained by taking its first derivative of the curve. That gives us the slope of the tangent drawn to this particular curve. Okay, so how to obtain the value of RF? I'm taking here. Alternatively, we know IDC is equal to IS into e power V by eta Vt, VDC by eta Vt. This is the curve equation, or I is equal to. You can write even I also, doesn't matter. Then slope of the, how to get the slope of the tangent drawn to this particular curve? Take its first derivative. What we write? Di by dv. It is just nothing but slope. It is equal to is into e power v by eta vt, and what is its value? 1 by eta vt. Is is a constant. Derivative of e power v by eta vt, it is just nothing but e power v by eta vt multiplied with 1 by eta. What is is into e power v by eta vt? That is just nothing but I. So I can further write it like I by eta. More precisely speaking, instead of this I can write IDC. So implies 1 by RF is equal to I. It is just nothing but 1 by RF. More precisely speaking, it is IDC by eta, or RF is equal to eta by IDC. That's it. This is how we can find it. It is like once the device is in operating, or once the device is in conduction, then if you apply small millivolts of signal, you can see slight variations in the voltage across the diode and the current through the diode. Those can be related by means of this particular equation, where did I write? IAC is equal to 1 by RF into VAC. It is not at all superposition, friends. With respect to DC, as far as the diode is concerned, we are writing V gamma, a voltage source kind of thing. But whereas with respect to AC, what is the equivalent circuit of diode? If you take further, right, with respect to AC means VAC, IAC, its equivalent is RF. Or I can write even like this, R suffix F, resistance. Okay, this is the idea. It is not at all superposition. With respect to DC, instead of diode, we write V gamma. Okay, or V gamma in series with capital RF. That's it. Whereas with respect to AC, we are writing small RF, whose value is eta Vt by IDC. By proper selection of the operating point, okay, depending upon the value of IDC, we can find the value of RF, the dynamic resistance of the diode. This is very, very important point of observation. Okay, if IDC changes, definitely RF value will change. Or I can say if Q point changes, the dynamic resistance of the diode will automatically change. Okay, this is known as small signal model of PN junction diode. What is the representation of diode with respect to small signal? Okay, further, how do we find this diode? See, now what we can write with respect to DC. 2 volts, 1.3 kilo ohm, and I can write IDC and VDC. VDC is 0.7 volts and IDC is equal to 1 milliampere. Okay. Next, with respect to Small signal AC. Individually, the device is not conducting, but with the help of DC, it is performed. Once the device is in conduction, then only we can write so. Sorry, it's not DC. I should write AC. Same 1.3 kilo ohms IAC and VAC. What is the equivalent circuit we are writing here? Okay, or you can, for better understanding only why I am doing all these things means, because at the very beginning you should understand all these points. Equivalent circuit, I am writing it like V gamma. One milliampere. Whereas here, what we are writing here, not V gamma, I am writing RF. In this example, its value is 25 ohms, and this current is IAC, and this voltage is VAC. So first, what is IAC? It is Vs by 1300 plus 25. Vs is 20 sine omega t millivolt by 1325. It comes around 15 sine omega t milli, sorry, micro ampere second. Okay, and what about VAC? VAC is equal to IAC into RF. 15 sine omega t micro into, means it is 0.375 sine omega t millivolt. Now you check this value. Is it not far less than eta Vt, which is 25 millivolt? Absolutely. Means the approximation I have taken is a valid approximation. VAC is far less than eta Vt. Okay, 100% it is true. VAC is 0.375 millivolt, whereas eta Vt is 25 millivolt. And the assumption I have taken is, or the approximation I have taken is absolutely true. Conditional only, not for all. Right? This VAC range, it is like 0.375. I can write it. And IAC, delta I said it is in the range of microamperes. Okay. This is the idea. So if I take IAC, it is something like this. And if I take VAC, it is something like this. Okay, it is 15 sine omega t microamperes. And here it is 0.375 sine omega t millivolts. This is the idea. So what about the total current I, or I suffix D? I mentioned here current through the diode. IDC plus IAC, and VD is equal to VDC plus VAC. Let us write those values. Okay. Now I can write I suffix D is equal to IDC plus IAC. IDC is 1 milliampere. IAC is 15 sine omega t microampere. Okay. It is just nothing but IQ. IDC means IQ. And similarly, V suffix D is equal to VDC plus VAC. It is equal to 0.7 volt plus 0.375 sin omega t millivolt. It is nothing but VQ operating point. Have you got the values or not? This is the procedure, right, using which we can find the AC components of current and voltage across the. This is known as small signal analysis. Okay, it is not superposition. Okay, the effect of AC can be studied from the values of current and voltage, especially the current you are getting from the DC analysis. The DC is responsible for the conduction of the device. After the conduction, the diode is able to respond to the millivolts of AC signal we are applying. Then the small AC variations of current and voltage can be obtained using this small signal model. A linear relation you can able to bring. It is always conditional. Again and again I'm speaking, it is conditional. If VAC or V input is very large, more than 20 sin omega t millivolt, it is like 100 sin omega t millivolt or 200 sin omega t millivolt, then right, you cannot apply such a super approximation like VAC by eta VT is far less than 1. Once that condition is satisfied, then it is a linear relation. Accordingly, the slope of that curve, slope of the tangent drawn to the curve can be obtained by taking its first derivative, or the regular method means this one, complete derivation. There are two ways to find this value of RF. Okay. So two ways to find the value of RF. Now, after setting the operating point, with respect to operating point only, you can see the variations of voltage across the diode and current through the diode. Those variations are very less, millivolts and microamperes of current. Okay, this is known as small signal model of diode. Now, let us have look at some problems based on what we have discussed so far.